So, as you've all just said, we are here to learn a little bit about Oded's mathematics, to celebrate his mathematics. As I'm sure most of you know, he was an amazing mathematician who managed with his mathematics to unify fields that people had never realized had such a significant and deep unification. And as we go through the sessions today, we will see some of the different areas in which he worked and some of the areas that he really created with his mathematics. So our first speaker is one of his principal collaborators, Wendelin Werner, who won the Fields Medal in large part due to their beautiful joint work on SLE. So, Wendelin.
Thank you. So, it's a very, it's a big honor and an emotional moment for me to be the first speaker at this conference. Can you hear me? Okay. And before leaving, I said to my friends, I'm going to this conference honoring Oded's mathematics, and people said, oh, that will be tough, 1 year after, and sad, and so on. And my answer was no. I mean, when you talk about Oded mathematics, when you open his papers, each time it's just a pleasure, and you are happy. And I'm sure that these 2 days will be just a happy moment that we'll be able to share by just, looking at, remembering his ideas and some tricks he learned us and he taught to us. Sorry, and so he and for those of us somehow who were not, on everyday life contact with him. We can all, I mean, his absence is very much, of course, felt, but nevertheless, his mathematics is really very vibrant and present all the time. And so before actually starting my lecture today, I spent some time thinking about, what should I tell to this sort of audience that we have today. You have some specialists who know very well everything about, for instance, SLE, which is the topic of my talk, and some non-experts or some people who don't know at all what SLE is about. So how can I, do sort of give a talk that will be okay for everybody simultaneously? And okay, Yuval and David gave us the instruction that we should, focus on some specific things, so little parts, try to show the beauty of some arguments, and somehow I felt, I must say that personally, at those moments during this past year where I felt, Oded's absence very much, what I did was actually that I played Sokoban, which is one of Oded's favorite games at the time when I met him in 1999. And it's this type of game where you have to push these boxes, and if you don't, the goal is to put one of these boxes on each of the red dots. And sometimes it's very tricky to find a route to do it, because if the box is, say, in a corner, then you're stuck. You're not able to push it anymore because you have to be behind the box to push it out, right? And I remember very well sort of the way Oded was looking. So Oded would look at this and just find the way without, just by knowing and find the trick. And we, amateurs, we just start pushing, move around and start pushing and see how this works. If we do if we're able to work our way out, and if he would see us find the trick, then he would smile and say, "Oh, okay, you're good, that's nice." But it's a very nice feeling when you find the trick yourself. And I think when we did mathematics with him, it was a little bit similar. So that he would know, he has some sitting above you and looking you play, and then sometimes he gives you the time to find the thing by yourself. And I recommend that you can download these things for free on the internet and play this on the plane back. It's fun. Okay. Anyway, so let me now sort of start with my actual slides, and I suppose SLEs, which is basically an invention of Oded, are, arguably one of his really most important contributions to science and to our scientific life today, and that students in graduate school will just hear about, I suppose, that Oded Schramm's SLEs. So the goal of this talk basically is not going to be obviously an introduction to SLE nor a full description of SLE, as those of us who had to teach this know that it's not, it takes time to actually, so it takes more than one lecture to actually give a real introduction, mathematical full picture of SLE and the arguments used. And actually, it's a great fun when you, you can actually watch, there are some recorded lectures by Oded himself where he describes this in his own words and own style. So there is this MSRI meeting where which is really nice to listen, because he, everything is very clear in his head, but when he explains it, somehow probably those who were present in that meeting maybe remember that his presentation of SLE was not the most transparent one, and that was really. But actually, if you listen now, when you know it, and you listen to everything he says, of course, everything is transparent. And the ICM meeting in 2006, for instance, his talk has been recorded, and you can hear him more recent times, 2006. And as I said last year, you can once you switch it on, you hear his singing voice, special tone, and you feel very much. It's very emotional. And also he wrote several beautiful introductional surveys about SLE itself. So the goal of this talk is not going to be just to try to do this, but I'd rather focus on actually, Yuval mentioned that, there were plenty of gems all around the place that Oded planted, but I would say that obviously one big diamond in the entire mathematical production is the paper that has been then later published in the Israel Journal of Mathematics in 2000, that he sort of put on the archive in April 99, where he basically explains what SLE is, and the entire talk more or less will be devoted to trying to show you that how much in that paper was already there, that the global picture was already, the frame for everything that happened later was already set. And also I should comment that Oded did not write so many papers, single-authored papers. He loved to share and to write joint papers with people. But this one is a single-authored paper, and in his single-authored paper, somehow he puts more of himself than in the joint paper. So when you read it, you feel that he puts more things like "I believe," "I think that," "this is nice," and so on. And this type of statements is not so nice, is not so often present in the joint papers, obviously. And always when he gives, some this type of statement, in retrospect 10 years later, you can feel how, perfectly right he was, and try to show you a certain some parts of that. And of course, I mean, for me, this paper was when the preprint came out, or more or less actually sort of 1 month before, when he sent it out, say, "Hi guys, here's a preprint. Please send me comments." Or at some point, then I felt, oh, now this is really important. And actually, in some way, I felt ashamed because when I met first Oded, that was when he came to visit Rick in Orsay some months before, and actually almost 1 year before, I think, and where he gave actually a lecture on SLE and the relation to loopy race random walk. And at that time, of course, I mean, I guess Rick was one of his main people he wanted to discuss with, because Rick had worked out some computations that enabled then in that paper Oded to actually figure out what the right parameter was in order to understand the scaling limit of loop arrays random walks. And I remember very well that the two of them, they were in very excited discussions, and somehow I didn't really understand what was going on. Was an outsider, and when he gave this lecture on SLE, I said good, but I didn't understand Loebner's equation, basically, and then, like most of us, it takes some time to, I mean, coming from probability theory, it takes some time to actually understand how this thing works. And then, basically, in that mail, when he said also that something, okay, and you will see that, I mean, he explains also that something important is going on here in this paper. So I missed completely, basically, the prehistory of how SLE was actually created in his brain and how the procedure went. And I guess Stefan, Itai, David, and Rick are probably those who saw it, by there and discussed with Oded during that pre or SLE formation period, and I'm sure they have anecdotes to tell about the genesis of SLE. Actually, Stefan wrote this. Where is Stefan? Oh, here. This how do you say, review? Memorial paper, or about and with full of anecdotes, some of which I stole from his paper and to put in my talk. And I recommend strongly that you read it, because it's great. So when you see something slanted on the slide, it means that it's just taken out of one of Oded's emails or of the paper. And basically, in the start of the introduction, so he sets the frame of, what is the scaling limit of a lattice model. Of course, this, was already discussed earlier by Eisenman and other people. And one little thing I want to mention here is this last sentence here, where he says, actually, it's important to discuss what the scaling limit is. And in his last sentence, he says, actually, I have a somewhat different definition that I will propose in the forthcoming paper. And I think the forthcoming paper in question is still somewhere in Stas's computer, because it has transformed into a joint paper of Stas and Oded. But I remember vividly that when I visited Oded a few months later, he told me something at the time I didn't understand either, like, actually the elegant way to look at scaling limit of percolation would be to, the set of quadrilaterals that are actually crossed by path, there is some topological structure, and these things are nice, and so this was already somehow present there. Of course, then combined with the fact that sort of so this was the frame for proving some scaling limit, and now the frame is also filled by Stas's proof of conformal invariance of percolation. So that's why sort of he waited until before showing this. And here there's also another very interesting sentence where it explains that basically the first task, and which is actually fundamental, is when you try to understand the scaling limit of a discrete model, lattice model on the large scale. Oh, I see you don't see. Is that you have to answer the following two questions. What kind of object is the scaling limit? What does it mean to be the scaling limit? And then and there's this nice explanation that actually there's more than one right answer. That it's not that there's one good way to look at the scaling limit and one bad way, but actually that there are several different ways to look at things, and that all of them shed sort of different lights on this. And so now maybe I start immediately with sort of the description. So, I mean, wouldn't make sense despite everything I said before, to give a lecture. I mean, to have these 2 days without at some point spending 5 minutes about what SLE is, right? So of course this will be just 5 minutes. But nevertheless, since SLE will be discussed, it appear in many of the talks during these 2 days, it makes sense to say this. And so in that paper, what he explains to us in an extremely clear way is basically how SLE shows up naturally in the context of loop arrays random walks. So basically, the idea is, okay, what is a loop arrays random walk? So imagine that you have a very fine grid here and in a very large disk, and you start a random walk at 0. So simple random walk, you start it from the center of the disk, and you condition it to get out. Yes?
I just thought a darker pen.
A darker pen, so I'll take black and green is okay. So, and you condition the random walk to go out at, say, this point here, 1. So here I take a very small, fine mesh grid, and so this is the unit disk, and you have a random walk, a random ant that moves on your disk, and it moves around, and you condition it to get out of the disk here, which is not such a big deal because it has to get out somewhere. You can always sort of more or less rotate the disk to make sure that that's what you see. So basically, and then you have this random walk, and then this object here gives a path that goes from 0 to 1, which is the trajectory of the random walk, and you can loop erase it. So along the way, each time you create a loop, you erase the loop, and in this way, basically, you're going to create, okay, now some sort of self-avoiding curve that joins 0 to 1, which is the loop erase random walk from 0 to 1 in the unit disk, which is a random curve that goes from 0 to 1. And there's a nice statement in Oded's paper that actually this model has been invented or created or much studied by Greg Lawler as a substitute for a self-avoiding walk, which was more difficult to study. And then Oded says, I think actually that loop erase random walk is as interesting as self-avoiding walk because of the connection to random walks and uniform spanning trees and all these things. So this is the type of statement that are not so present in the joint. But when he says, I think actually that, and loop erase random walk, as was sort of pointed out to us by many people actually, had been studied before. David Aldous, Robin Pimentel, Greg Lawler, David Wilson. And there's one property of the loop erase random walk that can be pointed out immediately. So imagine that so basically you have this is loop erase random walk from 0 to 1 in the unit disk, or discrete version of the unit disk. I could have another shape than the unit disk and other points than 0 and 1. You could adapt the definition easily. And the important property of loop erase random walk that he exploited was then that basically the following, that you look at the time reversal. So the loop erase random walk has a path going from 1 to 0. So you take the path loop erase from 0 to 1, but then you condition, you say, okay, I know that the curve is going to finish like this. You already know the curve is going to finish like this. So that means that the remaining path, I mean, the thing you don't know is basically the part of the path that goes from here to that point. And the key observation for loop arrays random walk was that actually, if you condition on this part of the curve, the law of the remaining guy is just the law of the loop arrays random walk from 0 to that point in the domain, in the slit domain, like when you take the disk and when you cut this out here. So in some sense, there was something preserved, preservation of some property when you were growing. Instead of looking at this path going from 0 to 1, as you would naively do, you look at it backwards, and if you start growing, discovering the information by growing the slit backwards, some law is preserved. So this is what is usually called the Markovian property of loop arrays random walk or something like that. Okay, so that was the first observation that was around before. And the second observation is Loewen's equation. So Loewen's equation is a basic tool in complex analysis that has been used a lot in the context of the Bieberbach conjecture. So an important complex analysis question. So the idea is the following. It goes as follows. Imagine now that I have a curve, gamma, that grows from in the unit disk from here to there. It's a simple curve. So at time 0, I'm here. At time t, I'm here. So I'm like, the idea you should think of it that you're cutting open the unit disk like this, going from here to 0. And the curve is then going to be parametrized in such a way that, so this is just coming from Riemann's mapping theorem, that basically if you define the conformal map from the unit disk onto the slit domain, so basically where here you have the unit disk like this, here, and here basically this unit disk is, these smaller circles are transformed into something like that. When you have this conformal map ft, that you normalize parameterize the time on the curve in such a way that f prime t of 0, so ft is such that ft of 0 is 0 and the derivative at 0 is horizontal, and that this is e to the minus t. And Loewen's equation just says that if you have this picture like this, here you have something like, which is zeta of t, which is ft minus 1, the pre-image of this tip here. That for each fixed point here in the unit disk, the motion when time evolves with which the sort of ft of z moves is given by sort of a smooth ordinary differential equation. Right? F prime t of z means the derivative with respect to space here. So I don't want to explain you Loewen's equation there, but basically this is already written in the abstract. It just says that basically there's a nice equation satisfied by growing slits like this that can be encoded by sort of as via a differential equation in terms of the conformal map. And the key observation by Oded was to say, well, actually, if you think of this and think of that together, then it's very natural. You get fairly quickly to the following consequence, that if you assume the existence and conformal invariance of scaling limit of loop arrays random walk. So that means you let delta go to 0, the mesh size go to 0 here. So this discrete random walk converges maybe in law to some random continuous function. And that if this is true, and if the continuous function is conformal invariant, which everybody believed was true, and which Rick partially proved to be true at the time, then the law of this scaling limit should be that of the curve gamma that you obtain there by plugging in zeta to be a Brownian motion moving on the boundary of the circle at a certain speed. So there's two remarks that one should make at that point, which is the first one, sort of a historical remark. It might be surprising, and is surprising for most of us in some point, that to use Loevner's equation to produce this, because this curve is a very rough and fractal type curve. You know, it's a scaling limit of something, so you would expect it to be a fractal type curve. And on the other hand, what you have over there is a smooth, it's a smooth ordinary differential equation. So how can it be that a smooth differential equation, gives rise to a rough fractal curve? And in a way, this type, okay, Stefan, of course, knows the story much better than I do. In a way, also in the complex analysis community, usually Loevner's equation was really used for smooth curves, because in the context of a Bieberbach conjecture, they were only using, it was enough to use smooth curves. Nevertheless, sort of in the 60s, Pomeranke and others had observed that you could construct rough curves using Loevner's equation. So, and actually he comments at the end of conjecture 1-2 in his paper is that actually the conditions here are true. Right? And he says actually it is plausible that perhaps soon there would be a proof of conjecture 1.2. And of course he was right, because a couple of years later the conjecture turned out to be okay. And so he predicted that there was no big, actually, conceptual obstacle somehow to be able to prove, to fill in the gap, to make this conditional statement into an actual statement. Okay, so now there's something I learned. If you are a probabilist and you were trying to understand the scaling limit of these curves, and you see the picture, and somehow this is what I thought, for a long time. And last month, reading Stefan's paper, I realized that I was completely wrong, because I thought, okay, you will hear the background of Oded in complex analysis. So obviously, he had all this, he knew all of this there perfectly, because that's the background you have in complex analysis. And he was, he interacted a couple of years with Itai, and Itai, persuaded him that actually probability theory was fun, and that there was a lot to do there, and that look at this, and let's do, and Itai can be very persuasive, and so Oded started to look at probability theory questions, and so he ended up pretty quickly on those parts of the probability theory that were touching a little bit to complex analysis, and that, of course, then he made the connection between what he knew from complex analysis and what he knew there. And this is completely wrong, because this is an email he sent, Oded sent 3 years ago to Stefan and Yuval when they tried to understand, how SLE was created at all. And so what Oded explains in that email that basically before working on SLE itself, he did not really know what Loevner's equation was. He knew vaguely that it had to do with that it was important, that it had to do with the coefficient problems, and that it involved something with the differentiation in terms. And then he says, well, I kind of rediscovered Loevner's equation in the context of SLE and made the connection. So, and if you know really Oded, when he says that you can be sure it's true, right? He's not claiming something. So it's obvious that actually he refound basically all these formulations. Actually, there was this other Loevner equation in the half plane, and that basically in the process of creating SLE, he went all by himself through the procedure to actually recover basically this type of theory that we have here. And I remember this paper of 66 by Pomeranke that he quoted, and that we quoted then because it was turned out in the joint paper. He said, well, actually, okay, we need to reprove it, and by the way, let me write the proof, because I have I think my proof is maybe safer, and so then he re-put his own way of looking at this characterization of Loevner chains in a geometric way in that paper. And I think this is a very important thing about Oded, that it's not, he didn't, when we say he merged together different fields or something, it's not, he did not just plug in, the missing thing, because he actually reconstructed all by himself both sides, as we will see also on probability theory, it's the same. And in the same paper, then he continues, and this, I love this sentence, so the one that is going to come, then he says, actually, if instead of putting a Brownian motion that runs at speed 2 times t on the unit circle, you put something else, something funny happens that maybe when the Brownian motion on the unit circle moves too fast, then the thing you construct is not a simple curve anymore. You know, instead of constructing some curve that grows here like this in a simple way, cutting something open like simple, this is not exactly true anymore when kappa is too large, and in that paper actually proves that when kappa is larger than 4, indeed, it's not. So the phase transition at kappa will equal 4 was, so he says, when kappa is larger than 4, it's not a simple curve anymore. Here's a proof, and I conjecture actually that this is actually kappa equal 4, the right is actually the correct phase transition. And then this sentence, given some kappa, even when kappa is not, so that means even when this is not a simple curve, the process is quite interesting. And so I don't know if there's something, you know, in Hebrew that makes this translation, you know, what does it mean to be quite interesting? You know, because everything that happened later had precisely to do with this quite interesting object he creates. Of course, you know, if you invent something, you are not going to say this is very interesting, but Oded would not do that, but he says it's quite interesting. And I remember then, you know, I was remembered by this last year. You know, the last email I got from Oded is the following. That was after a conference we organized in Montreal. And he said, Chuck, John, and Wendelin, we are the 3 who organized it. Thanks once again for organizing this workshop. I think it went very well, and it was quite worthwhile. So then I thought, well, okay, then quite worthwhile, you know, especially that, you know, they thought it was quite worthwhile to make a trip to a conference. And I very much remember last year when I said, quite worthwhile. I've seen this quite before already in Oded's, and actually sort of, okay. And then comes what sort of made me tilt in some you know, when I said, okay, now this is really going to be important, because then he says, in fact, I plan to show in a subsequent work, assuming a conformal invariance conjecture analogous to conjecture 1.2, that actually a similar process described the scaling limit of the outer boundaries of percolation clusters. And he also, he will describe it, everything. And actually, in the paper, he actually already sort of explains everything more or less, what he planned to do at the time, and that this sort of implied many things, would imply sort of at least explain many things that appeared in the physics literature having to do with the scaling limit of percolation. And so for those of you who don't know percolation, this is one of the pictures that Oded created and that is used all over the world. Basically, which is this interface, the scaling limit that is going to converge to one of these SLE processes, which is basically you have these hexagons, you toss a coin, each one is colored in gray or in white, and then you follow the boundary of a big island or connected island of black hexagons. You follow that boundary, and this is this black curve that had been also okay. That's the percolation boundary, and understanding sort of the large-scale property of this curve was a big problem that the physicist gave us to bite on, and that we had at that time looked pretty stuck. We were very stuck. Okay, and just a comment on what Oded was sort of aiming to prove at the time. I mean, what he was promising to put in this later paper, and somehow the later paper, got delayed because, then Greg and I sort of showed up and say, let's prove this because with your thing you can solve our problem. And then Stas came with this proof of conformal invariance of the discrete model, and then sort of the conditional thing was okay, and so it didn't make sense then to write that paper. He promised, but I just want to say that how did he knew that kappa equals 6 was the right parameter? Basically, there's the following thing. It's just the following argument. If you have some symmetric square like this, or some symmetric object like this, if you look at SLE sort of any parameter going from here to here for when it's a SLE that bounces on the boundary, basically it will have probability, but simply because of symmetry, it will have probability 1/2 to hit this part before that part. It's just black and white are symmetric in the previous picture, so if you start with a symmetric picture, it has probability 1/2 to go more to the right than to the left, or vice versa. So this is okay, but then if you do what Oded already computed at the time was something like, okay, suppose now that I take my SLE that goes from here to here, instead than going from here to here. Right? I take the curve that goes from here to here. Remember, the curve is defined, but you have to decide a priori where the starting point is when the end point is. And so he did the computation basically in that context of what's the probability you first go hit this guy before that guy. And there's something very special about percolation, which is that basically the fact that this guy is colored in white or black, or this one is colored in white or black, is not going to influence the curve that you are going to draw inside the domain. And so therefore that for percolation or percolation scaling limit, the probability that the SLE from here to there also has probability 1/2 to hit that before that. This happens only for kappa equals 6. So basically, you could change slightly. You can move the target point you are aiming at, and certain probabilities would still be preserved under this moving of the endpoint you look at. And so basically, this is for those who know the story. Then that came later. This is basically that he actually already had some pre-locality statements just looking at Cardy's formula that he computed for the various values of kappa. And so that it was no surprise that when we said, oh, actually, can you prove locality of SLE? He said, yeah, I know this is doable, right? And he already had this type of argument in that paper also. And at the end of the introduction of that paper, what he explains us is that the following, that, well, the big picture, the emerging picture is that different values of kappa in the differential equation that we wrote there produce different paths which are scaling limits of naturally defined processes, and that these paths can be space filling or simple paths or neither, depending on the parameter kappa. So space filling is this has to do with the uniform spanning tree model that I don't discuss here. Simple path is kappa smaller than 4, and then you have this intermediate phase, which is this neither corresponds to kappa between 4 and 8. So he has already set the entire, now, the goal will be to prove all these different things and now I want to emphasize one thing. Experience of Oded, sort of also present in that from that paper, which has to do with his relation to probability theory and to stochastic calculus. And so in the proof of that paper, where he proves that basically it's not a simple curve as soon as kappa is larger than 4, for that this procedure does define actually objects that are not simple curves, but that are still probably quite interesting. What he writes is the following. We now show that a certain function satisfies the second order differential equation inside E in an interval using Ito's formula. And then he gives the following thing. The reader unfamiliar with stochastic calculus can have a look at, and then he gives a reference, for example. Or he can try, so if you are the reader unfamiliar to stochastic calculus, can just try to derive it directly. Yeah, you can just, invent stochastic calculus on your own, why not? And then he explains, the latter is a bit tricky, but can be done. Right, so basically what he did at the time was that well, he just probably did on his own, the entire understanding of how you get the second order differential equation. And actually, I remember now that since I'm at Microsoft, I can say that when I discussed with him, a priori we were saying, well, if you're working at Microsoft, or if you were going to work at Microsoft, how do you do? Because there's no library. And at that time, digitalized things were not so present, 1999. And obviously, not having a library was not such a problem for Oded, because he would just, the library was just more there for, to cite the appropriate references and give credit to appropriate people, but he would, always derive things first, understand things first by himself, and it doesn't look like he would read them out from a book or stuff. And actually, this funny thing then that continues the later page, which is, so he completes the proof of this equation here, that this should satisfy this. And so the way he does it is assume that the function is C2, and then apply Ito's formula, and that's just for those of you who know stochastic calculus, and then you end up immediately with that equation. And then he said, well, actually, there's a problem here if I apply Ito's formula, if I don't derive it directly, that I haven't proved that this function that is defined by being a probability of a certain event is actually C2. And then he says, well, there should be a reference, so that's in this version 1 of his preprint, implying this, but we have not located one. Okay, so how does he do? Well, to deal with this, here's the way. So I'm sorry, I didn't find the appropriate reference, but here's why it is C2, right? And then he explains the thing that, well, you don't need to know that it's C2 because you just, once you know the function and you put it in, the solution to the equation is C2, you plug it in and you verify that indeed by using the stopping, and that's actually the way, standard way it is proved. So again, sort of, he didn't know where to find this, but he said, well, that's the way to do it, actually, is a better way. And actually, I very much remember with Greg at some point, well, actually, that's just a funny thing we just discussed on the parking lot of Homestead Studios with Greg this morning. And we were sort of saying, well, actually, sort of when one tries to discuss, our joint papers, that has, the things where you had to prove technically things, somehow it was not so interesting to look at those because the proofs were improved later on and simplification were found, so in those technical aspects. But actually, in this paper, basically nothing. There's nothing that you want to. In this first paper, everything is still, like it should be. So there's no real update, except of course that other things were proved later on. But you don't want to really replace the arguments that he produced. And in one of our technical papers later, there was a tricky question involving precisely Ito's formula, but differentiating whether you could apply these things uniformly when you had a family of Ito things, and differentiating with and sort of I was scratching my head and saying, well, I don't know any reference for that. Is this true or whatever? And Oded said, yeah, of course it's true. Of course this is going to be true because uniformly you can differentiate. Okay, and then. I was supposed to be the one who grew up in stochastic calculus and who was supposed to be able to swim, or speak the language fluently, and then we managed to find a reference actually that saved us of having to reprove it. But so he really was had his personal understanding, which he understood it. And then just to finish, maybe I'm actually too fast in my lecture, but again, sort of when he says it's a bit tricky but can be done, it's very interesting because in one email exchange that he had with Stefan and that Stefan forwarded me, he shows basically how he thinks about it shows it's not that the content of what I'm going to show you is important. It's more the way sort of he understands it and the style with which both the style mathematical and gentleman type style with which he explains it in email. And I'm sure all of you who interacted with him had this sort of email exchanges where he gently, explains to you on the email an argument. And so basically, they were discussing the relation between the generator and the differential equations that pop out, and the stochastic differential equations that you had before, which had to do with this, which then turned out to be these equations I wrote later. And Stefan says, well, is it easy to see, right? So you say, and here's the answer of Oded. So you'd probably look up some book on the relations between PDE, SDE, and operator semigroup, because my background in this stuff is not as strong as I would like. So that's something very funny, because I always felt that he had this, he would have liked, to be really, and he always felt these guys, doing stochastic analysis and probability theory, maybe they know something I don't, or, they. So he would have liked to have a strong background there, but I'll give you my understanding for the little that it's worth. And then he gives two ways to look at this. So, and that's the way sort of he was looking at this type of objects in the time where he was, that's not the, it's just at the same moment where he was, working out all these things by himself. So of course, later on he would have explained it in a completely different way, but it more shows how, the way he created these things. So you don't have to read this, but then he says, here's one way. And so he explains this, and he says, you have this density, total mass is conserved, you differentiate here, and assume it's smooth, you can differentiate, you substitute, and your hand-waving argument, and that's what goes out of this. In a way, I would say this is more in the stochastic calculus version. And then, so much for this approach, now another one. And then basically he completely says, well, anyway, this problem is a linear problem, so we can, divide it, sort of step by step. So let's first look at what happens if there's a uniform density to start with. Let's first, look at what happens if I have a drift to the left on the one side of the domain on R plus, and a drift to the left on R minus. Well, then the singularity piles up, and this will have to do with the derivative. And so he basically explains all the E2 calculus just by, it's linear, and then all the terms are coming out, just by looking at them one by one, and that's what it is. So that's the reason for that term, for instance. And I like very much the third one also, which is, actually I had a third way, that's everything, that's his answer, right? So sometimes you got answer which is very, to think of it through approximating the motion, which is diffusion, of a random walk on a grid, which was not evenly spaced. But I don't think it will be helpful for you if I try to recall that. So, of course, for those of you who know, so he had all this picture and everything. It's interesting that he works with his entire, his own object. So simple random walks, I understand, I do this. So he always has some feeling for the object that he plays with. And okay, and then, of course, I like the, gentleman touch, sort of. I hope this was at least a bit helpful, right? The type of thing when he explains you something, obviously, it took him, I don't know, 40 minutes to type this long thing trying to explain you gently, and he did that, recurrently to probably all of you who interacted with him, and always, just saying, this is the way. Try to explain, but maybe I didn't succeed. Sorry if I didn't. And actually, okay. And so I hope that there's really one thing important thing that I understood. In a way, I felt it when I interacted with him, and then when basically I was understood that even Löwner's equation he basically recrafted on his own. No, of course, I mean, okay, I should not say that. I mean, the fact to use Löwner's equation in the context of DLA and other contexts was, in the air, there was Carlson and Makarov, and but basically the way he wanted to understand it was just by re-understanding or reproving everything himself. and that this was not just, I saw it with my eyes that this is the way he proceeded in probability theory and stochastic calculus, but it looks like, that was like the same way in actually all areas that he touched, or many areas that he touched. And again, so I want to emphasize really that it's just a pleasure to read his paper and his prosa, and when this type of sentences that I showed you, it's quite interesting, or I believe that this is worthwhile or something. You always smile when you read these things, when you know Oded and when you knew Oded, and you read his papers and you smile, and actually sometimes you laugh. So I told you, I said, for instance, to my family, I'm going to Oded's memorial conference, and I have to prepare actually my talk. So I was just sitting in the sofa of my living room, reading his papers, and the very same sofa that I was, were last year devastated when I learned, that Oded fell from the in the mountains, and I was just reading this, and I was just laughing, I was just smiling and laughing, and then my daughters came along and said, "Well, what is it that is so funny?" I said, "We want to tell us," and said, "Well, actually, I'm reading just a paper of Oded, and it's just nice." And they were looking at me like, something is wrong. He tells us he's going to a memorial conference. This looks okay, sad moment, and he's just laughing or smiling by reading his papers, and. But really, I mean, it's just I just recommend to all of you sort of to, when you fly home, or that you just print out the Israel Journal of Math paper, or rather the version 1 of the preprint on the archive, or actually Oded's sort of ICM paper is also a very nice thing to read, because he just gives plenty of problem to the community. Some of them have been solved by now, because that was 2006 and now it's 2009. But sort of he just wants to give problems, and also explaining things in a gentle and simple and transparent way, not hiding anything. There will never be something that you have the impression that he didn't want to share. And also, really, if you want to feel a little bit like Oded probably felt every day when he proved or found the tricks, because that's one other thing when you interacted with him that Stefan writes, was that you can just see how fast he found the tricks or went around. There was let's try this way, it doesn't work, okay, and the rest of us would just feel okay, this proof breaks down completely. We don't know how we are stuck, and 2 hours later, actually here's another way, or maybe we can go around the mountain and climb the other. And so the speed with which he would find the trick and solve the concrete problems that we were working on. And if you take one of these Sokoban things, sort of that we have here, and if you play a little bit around, and then you find the trick and say, oh, you have first to push the boxes in that way and then the moment when you find this, then I guess you feel a little bit like Oded, and probably felt you smile, you're happy, and that's it. You don't make a fuss out of it. You're just because you are in front of your and you're happy to actually also maybe then share it with somebody who went through the same thing, and I guess that's okay. My recommendation: you download it and you play it on the plane back, and it's fun. Actually, it's interesting because Sokoban, in a way, if you start playing with this, it's not completely unrelated to the entire Werner story and so on, because once the box is or even with the the other Kober problem or something, because once the box is on the boundary, somehow you can't push it out of the boundary anymore, and there's something growing. It's not completely unrelated, and maybe the time Oded spent playing like this Sokoban was very useful for all of us to in the way he crafted then SLE. So okay, and thank you very much. I'm not sure that if there are questions or what comments, or if you, I don't know if Rick or David or Stefan or Itai want to say something about the...
I want to say something. So, just about your first comment. So, in '97, a bunch of us were going to a conference in Italy, this is shortly after we worked with Oded, Itai, and Russ Lyons on uniform spanning trees, and then Oded consulted me and said, well, I want to talk about something a bit speculative, and this is '97, and he presented a large part, not everything, but a large part of what was eventually in his Israel Journal paper. This was already in '97, but then more pieces were missing, and he described it to me, and I said, this sounds like total science fiction. 100 years to do. We could talk about something more secure, and he did accept that advice then, but that's, maybe when he had the picture. And the other thing that's related to the stochastic analysis story is at some point, this is between '97 and '99, I get, from Oded emails asking, actually pretty basic things about Brownian motion and its characterizations. So, Paul Levy had characterizations of them, and Oded just, as he didn't know this literature, he rediscovered these and because they arise exactly in the story that Wendelin was saying that this, and then he asked, what's the reference for this properties of Brownian motion? So it's not that he combined these known things. He realized, okay, we need some proper characterizations of Brownian motion in order to prove what we need for the first. Any other comments or questions?
Yeah, maybe I'll just one other comment that when somehow my first experience with Oded was sort of when we had this hike with Rick and in Fontainebleau, and maybe that was one of my first experience of a mathematician that would actually love to do mathematics on a hike, right? So that the two of them were just, it was a bit frustrating because I didn't understand what was going on. And so they were discussing maths during the hike in a very, I remember sort of also that probably Greg also remembers that somehow the proof of loop race random walk convergence in the end just took place at this MSRI conference during a walk when we decided let's walk down, from MSRI down to Berkeley. And when we started on the top, we started discussing this, and down it was okay. Yeah, looks like it's doable. We know nothing is preventing from us from anything. So he loved, and I guess, to talk really mathematics also, while walking, or by being sitting really like in his chair, in this sort of low sofa. I guess at Microsoft you have plenty of those, where just like hands in his pockets, and then say, well, actually I don't think that, and then providing you the argument by sorry for my handwriting is not good, but I will try to sketch it on the blackboard, and then and so things were went always pretty quickly. It was not like he was, the ideas were not, took hours for them to show up. It was like interaction and discussion, which was also ignition for his creativity. Yeah.
Thank Wendelin.